So that happens in a lot of classes. Fridays tend to be usually Monday, Wednesday. Yeah, I hope that. I'm afraid we'll probably have to do it this next semester. Quite a few people online last Friday. It's 11 to 5 now. I went to 6. There's like 23 people online.
Professor,
Yes?
I have a quick question before we start class.
Sure, go ahead.
So there was a theorem that we went over maybe a couple lectures ago,
Yes.
and it states, suppose V1 through Vt are linearly dependent, then
Yes.
at least one vector is a linear combination of the others.
That's correct.
Wouldn't that be, it says at least, but shouldn't it be like every single vector in that set could be written as a linear combination of the remaining in the set as well?
Well, no, because you could have one of, when you write it as a linear combination of the zero vector, one of the coefficients could be 0.
Okay.
At least one which is not 0. But you could have one of the coefficients be 0.
Okay, which eliminates the vector.
Right. Which you would
Okay.
divide out by zeros.
Okay, thank you for the clarification.
It's a good question. Okay. Looks like the sound is good. So let's see. Maybe we can start pretty soon. So were you able to turn in the sign over there? Yeah, well, that's pretty smooth. Yeah, I kind of hit you with it. I mean, at the beginning, I sort of hit you with 3 sections. I had to do that so that it's back off most of the semester. You'll notice the homework is a little bit less. So I understand that at the beginning, you have to do some of the, a few more sections. How much?
Like this last one, it's just long on my iPad. I looked at it, I'm a lot away.
Yeah.
So,
Well, it's really good because I can't emphasize enough, how much important. We've really gone away from that. I think it hurts.
yeah, I like math. Math is all about practicing.
And I just don't see why, you know, like, I just don't see why, you know, we should, your time is valuable. And so I'm trying to think of ways to make your time efficient and most effective. I don't want you to do like computerized homework and not have this review. I know you're taking other classes, I know you're busy. Okay, so maybe we should start. Okay, so we're going to start a new topic today. On the iPad. All right, great. All right, so today what we're going to do is we're going to switch a little bit and talk about functions and linear transformations. So beforehand, we were talking about systems of equations. We will actually tie this in later on. But right now, I just want you to think about maps or functions between certain sets. So, we just have to switch classes. Okay, much better. All right, so the topic of today is linear. What's happening there? Okay, so some reason transformations. Oops. Hang on, let me just try to see if I can do this. Okay, let's see if that works better. Fair enough. All right, let's see if that works. Okay, so the first thing I want to talk about is the idea of functions. And so what is a function? Well, it's an assignment. So if you take a set X here and a set Y, what I want to do is I'm going to take everything in X, an element of X, to exactly one value inside of Y. So a function sort of maps things across in this way. So here's X, little X here, and this is f of X over here. Okay, and you've seen lots of examples of functions, and we'll actually go over examples in a moment. So let me give you the formal definition. So f from X to Y is a function if f assigns to every x and x exactly one value y. So a unique y and y. And y here is equal to f of x. Okay, so basically we don't want to take x to two different values. All right, so just a little terminology. X is called the domain. Okay, so that's where you start your function out at. Y is called the range. So imagine like you're an archer, for example, sitting at X, and you're shooting arrows in a Y. Okay, so Y is kind of your target that you're actually looking at. Now, what elements are actually hit by the function? That's called the image. So f of x is called the image of f. And by definition, it's a set of all elements in y such that there exists an x in x with f of x equals y. Okay, so basically, if you're shooting these arrows into your target, everything that's hit in the target is in the image. Okay. Now, what is the inverse image equal to? So the inverse image. So what you do is you take a subset inside of y, and then basically you just sort of look at all elements in x which are mapped into S. So f inverse of S is the set of all x in x such that f of x is inside of x. Okay, so the picture looks something like this. There's y, there's like the set S, there's your set x over here, and then you just look at all elements of x which are mapped into the S. So you look at all the things which are mapped into S. Okay? And those things are in the inverse image. This is the inverse image of X. Okay, any questions? All right, so let's do some examples. So in calculus, you looked at real valued functions. So why don't we just look at some of those? And we'll just apply some of the principles that we were talking about. So there are some examples. So one, I have f of x equals to the sine function. Okay. So this function takes real values and sends them to real values. So f, the domain is R, and we can specify the range to be R2. Okay. So let me just draw the picture of the sine function, just so that I remind you what it looks like. So the graph of the sine function looks like this. It oscillates between 0 and 2 pi. And the amplitude is 1 to minus 1. This is the graph of the sine function. So this is y equals sine of x. All right, so what is the image of this function? Anyone?
Oh, this is a guess, but a wave?
Well,
Is
I mean, it has to be inside of the real numbers.
Is it -1 to 1?
Yes, exactly. Right? I mean, it's just all things which are hit by the function. So the values between -1 to 1 are actually hit by this function. Okay? I mean, I'm never going to hit 2, right? Sine of x is never equal to 2. So 2 is not in the image. Okay, does that make sense?
Yes,
All right.
I just thought you said image instead of range.
Yeah, the range could be like R, right? I mean, you don't hit necessarily everything in the range.
Yes, okay,
Okay.
thank you.
All right. We'll do some more. So f of x is equal to the natural log of x. Okay. And you've seen this one before. So here's x, and here's y, and here's the natural log. All right. So first of all, what is the domain? what x values can we plug in?
Domain is from 0 to positive infinity.
Right? Okay. Ah, thanks. Okay. And what is the range?
The range is from negative infinity to sorry, it's -1 to positive infinity. Or is it positive infinity or is it a number?
Well, it's just all real numbers. And you can just, you know, I mean, you can make your range as big as you want. There's no like absolute answer for the range. Okay. But there is an answer for the image. Right? So what's the image of the function? What values can that function hit? What values of y can that function hit? Negative infinity to infinity, right? So it's all real numbers. That's not an asymptote, right? It can go on forever. Okay, any questions on this? All right. So now I want to make a definition. So definition. So a function, let's say f from x to y is onto if and only if the image is actually equal to the range. Okay. All right. Okay, so let's look at these functions. So is number one onto or not? So is the sine function onto? Is
Yes.
the image equal to the range? I heard somebody say yes or no.
No.
So the image is -1 to 1, right? Inclusive. The range is R. So those two are not equal. So you don't hit every single y value, so it's not onto. So this one is not onto. Okay. What about number two? What about the natural log? Is it onto or not onto? Is the image equal to the range?
It's onto.
Onto. Very good. Okay. We've done the work already, so you can just look at it and check. All right, let's go switch back to black here for a second. Let me make another definition. Yes, here's another definition. A function f from x to y is called one-to-one if and only if given f of x1 equal to f of x2, then one has to have an x1 is equal to x2. Okay? All right. So let's go back to these functions over here. Now, is number one onto one-to-one or not? So basically, you're asking, if I take two different x values, can I get the same y value?
Yes.
Yes, you can. Okay. So it's not one-to-one. So this one is not one-to-one. Okay. Now, how about the second one? Is it 1-to-1 or not 1-to-1?
It is 1-to-1.
It is 1-to-1, good. So one way to sort of check this for these type of functions is you just take a horizontal line. And if it cuts across the graph more than one time, then you know it's not 1-to-1. Okay? So if the function is like strictly increasing or strictly decreasing, it has to be like 1-to-1. Okay? All right, good. Let's see. Why don't we do some other fun examples? So we have an example which is not onto and not 1-to-1. So maybe we can just play around and do a few more examples. So let's see. When we look at one which is not onto but 1-to-1. So I want to have a function which is not onto but 1-to-1. Okay. So can anyone sort of think of a real valued function which actually is like this? Well, why don't we take, I don't know if this is the best one. You could probably get another one. But let's look at the arctangent function, for example. So this is a function which has an asymptote at pi/2 and -pi/2. Right? So it kind of looks like this, where it kind of goes up and kind of comes down and approaches the asymptote. Okay, so let's call this f of x. And f, we can take real values and we'll get some real value out. Okay. And so this is 1-to-1, right? Because I mean, you only get one y value for every x value. Yes. And is it onto r? No. So because f of r goes between -pi/2 and pi/2. Okay, so this function is not onto but 1-to-1. Okay. And then we have one last case to do, right? So we have not onto, not 1-to-1, onto and 1-to-1, not onto but 1-to-1. So what else is left? We have not 1-to-1, but we want onto. Okay. Well, you can, anyone want to venture to give me an example?
Could 1/x² be 1/2 or not 1?
1/x². No, I think that's always. I think that's always 1-to-1. But what if you take a polynomial like this, with like, well, let's say it kind of comes down like this and goes like that. Okay. So this is certainly onto, right? Let me make some roots. Let's say it has a root at 1. Let's say it has a root at -3 and a root at -2, for example. Okay, so it's a cubic polynomial. So we can write this out. So that's going to be y. And okay, so what are the roots? 1, 2, -2, and -3. Okay. So you have this cubic polynomial like this, and notice that's not 1-to-1 because if you take a horizontal line, it'll hit the graph twice or 3 times sometimes. Okay, and so it's not 1-to-1, but certainly onto. So here f goes from r to r, and the range. The image is actually equal to r. Okay, so this gives you examples, at these real valued functions of 1 to 1 and on. Okay, any questions on this? All right, now what we're going to do is we're not going to study arbitrary functions. We're going to study what are called linear transformations. Okay. So linear transformations are going to be related to matrices, but let me start with the more general definition of a linear transformation, and then what we'll do is we'll show that it's sort of equivalent to looking at matrices. Okay, so here's a general definition. Okay, so a function, let's call it T, from Rn into Rm. So I'm taking vectors in Rn, I'm taking mapping into vectors in Rm, is a linear transformation. Okay? If two things happen, just if and only. Okay, so the idea is that we know that we have vectors, Rn, we have vectors in Rn, and what can we do with vectors? We can sort of add them, and we can take scalar multiples. So the linear transformation has to be compatible with those operations. So the first thing we have to impose is that if I take two vectors, v1 and v2, then the function just sort of is compatible with the vector addition. Okay. And two, we want it to be compatible with the scalar multiplication. So this is going to be lambda times t of v. Okay, so I guess v1, v2, and v are in Rn, and lambda is 1. Okay, so this is a very special type of function which is compatible with vector addition and scalar multiplication. Any questions on the definition? All right, so you've actually seen linear transformations before, and let me just give you how to construct a linear transformation. Okay, so we're going to start with a matrix. So let A be an m by n matrix. Okay, and then with this matrix, I'm going to define a linear transformation. So define A, and where's A going to go from? It's going to go from Rn into Rm, and I'm going to define it as A times X. Okay, it's exactly what you've done before. You just take the vector X, and then you multiply x1 times the first column of A, x2 times the second column of A, so forth and so on. We'll do an example in a moment. So more specifically, let me just give you an example. So let's just do 3, 1, 2, 1, 3, 2. So we're just an example of numbers. Okay. So this should be map. Ooh. I'm supposed to do that. Oops. Okay, so let me deal with meter here. Okay, so A will be a map from R3 to R2. Okay. And so I'm going to take a times x. So this is going to be equal to a of x. And so what do we get? So I take a, and I'm going to multiply times 3 tuple. Okay. And remember what the definition was. It's x1 on the first vector, x2 on the second vector, and x3 on the third vector. Okay, so we're using the operation that we had before to create a linear transformation. So any matrix in by a matrix will give you a linear transformation. Okay, questions on this? Okay, so let me give you some properties of linear transformations. These are some properties. Okay, so the first property is, so first of all, I have a t, and I guess I'm going, let me just make sure I get it right. So Rn into Rm, and I'm assuming that's a linear transformation. Okay. So property number one is if I take t on x on lambda 1 v1, lambda 2 v2. So I'm going to take a linear combination of vectors. Let's call this lambda t v2. Okay, so I get a linear combination of v1, v2 up to vt. Then what I can do is this is lambda 1 t on v1 plus lambda 2 t on v2 plus lambda t t on v. Okay, so so you can see, I mean, the linear transformation is going to respect linear combinations. Okay, that's a way to remember. And then secondly, if I take the zero vector, this always has to go to the zero vector. Okay. So what I mean by this is the zero vector in Rn has to go to the zero vector in Rn. Okay. All right, so let's do an example where we work with linear transformations. Okay, so let A be equal to the matrix 1, 0, minus 1, and 3, 1, 5, and minus 4, 2, 1. And B be equal to the vector 0, minus 5, 6. Okay? And what we're going to do is we're going to set, let's say, A of x to be equal to A times x. So A is a linear transformation from R3 to R3. So this is a linear transformation. Right? So my question is B in the image of A? So question is B in the image of A? So I guess I'll just call it A of, I guess, R3. Okay, so this is the image of A. All right. Okay, so can anyone say or describe, I'll put a question mark here. So this is the question. So can anyone sort of describe how to solve this problem?
Do Gaussian elimination and see if the system's either consistent or inconsistent.
Okay,
Determine if it's limited.
that's correct. So I just want you to back up a little bit and kind of explain why it would reduce to Gaussian elimination.
Mainly to see if we'll have, or we'll end up with like a 0 equaling a non-zero for B.
I just want you to back up from the question. I want you to connect the question to the Gaussian elimination in terms of, I mean, you're correct in terms of the answer. I just want a little bit more justification from the rest of the class. The intuition is absolutely right on. But so let me ask you this. So if I want to know whether B is in the image of A, right? So let's kind of back up a little bit. Okay. So B in A of R3, let me put this as a question mark, is equivalent to, is there an X in R3 such that AX is equal to B? Okay? Do you agree with that? Yes?
Yeah.
Yeah, okay. So to ask whether something is in the image, I'm trying to find an X for which AX is equal to B, all right? And so we know what that entails. That's solving a system of equations. Therefore, this question is the same as solving and a system of equations. Okay, so we want to actually see whether the system is consistent or not. So if the system is consistent, then the answer is yes. If it's inconsistent, the answer is no, right? So now we can apply the Gaussian elimination and do exactly what you said. Okay, is everyone clear on how we deduce this? So again, it's this kind of problem where, we have something which is kind of abstract, and we want to reduce it down to some Gaussian elimination computation. Okay, so let's kind of do this. Okay, so I put the matrix A here. Okay, here's B. So I want to know whether this system is consistent or not. Okay, negative, -4, 2, 1. So just make sure it is correct here. Make sure, oh, -5. Okay, I have a -5 here. I think it's all right. All right, great. So now what we do is we just turn the crank. Okay, so I'm going to multiply the first row by -1 and add it to the second row. So 1, 0, -1, 0, 0, 1. Let's see, -5 minus is -2, and we have -5 here too. Okay, and similarly, I'm going to multiply the first row by 4, and add it to the third row, and then put the result in the third row. I get 0, 2, see, -4 plus 1 is a -3, and let's say I get a 6. Okay, everybody all right with that? Okay, so we only have to do one more step. So here's -1 over here. Okay, so we have 1, 0, -1, 0. 0, 1, minus 2, minus 5. And I only have a 0. Oops, I only multiply this by minus 2. I'm sorry about that. That's my multiplier. I get 0 here. I get 4 plus minus 3, which is a 1. And I get 10 plus 6. Is that right? That looks right. Okay, so that's 16. All right. Okay, so what's my conclusion? Okay, so therefore, the system is consistent. And has a solution. Thus, B is in the image of it. Okay, any questions on this?
I have a question.
Sure.
Could you clarify the difference between in the image of A and in the span of A?
You know, you're asking a really good question because the answer is it's the same.
Okay, that's what I thought.
But we have not, but we have, that's a very good observation.
Yeah, I was also confused about that.
Yeah, so it's right. So let me just write this down. So the image of A is equal to the span of the columns of A. Okay. I guess you can kind of see that back from back here, right here, right? So if something is in the image, if and only if it's going to be in the span of the columns. Okay, right? So that's a very good observation that you made. Good. Other questions? All right. Okay, so now what we're going to do is, I guess this is not so hard. Actually, I want to do. Let's see, I just want to. Okay, so we'll probably do this next time. All right, so let me give you another example. Okay, so let A be equal to -1, 0, 0, -1. Okay, and so let's let we'll call it T go from R2 to R2, and we're just going to let T of X be equal to A times X. Okay, so normally I denote it by A, but I'm just going to denote it by T. Now, U will be the vector 5, 2. Okay? And V will be the vector 3, -1. All right, so what I want to do is I just want to plot. So the question is to plot T of U and T of V. Okay, so we want to see what this linear transformation really does. Okay, so we're working with R2. So here's X and here's Y like this. Okay, so now we can pull out the colored stuff. So I don't know. George is not playing this week, right? Next week? Yeah, we'll just kind of prepare. All right, so let's plot U and V. Okay, so 5, 2. So 5, 2 looks something like this. Okay, so let's say this is the vector U. Okay. And B looks like what? So it's 3, and I have minus 1, right? Okay, so it looks something like this. Okay. So these are the two vectors, right? So let's see, what is T of u? So T of u is going to be equal to, I need to put this matrix back up here, minus 1, 0, minus 1, times 5, 2, right? So this is 5 times minus 1, 0, plus 2 times 0, minus 1. Yeah. So the answer is going to be minus 5 minus 2. All right. Okay, so that means the vector here is sort of, the T of u goes this way. Okay, so you just sort of reflect along the line of y equals minus x. And then similarly, I'm not going to do this computation, but you can just imagine it's what, minus 3, 1. Okay? So it's harder to kind of draw. Let's see. We go like this. Minus 3, 1. So it's like this. There's a T. Okay, so any questions on this? All right. Okay, so maybe I'll do one more example. I may not give all the details, but okay. So suppose that the linear transformation goes from R2 to R2, okay? And T of 1, 5 is equal to 2, 0. And the linear transformation takes 3, 1 to 1 minus 4. Okay? So the question is, where does 6, 3 go to? Okay. So we have a little time. I'll actually set this problem up, and then we'll finish it off at the beginning of next class. So let's think about this a little bit. I'm not given exactly where 6, 3 goes. So can anyone sort of tell me how we can use the data that we have where these two vectors go to actually tell me where 6, 3 goes?
Are we gonna have to find out what A is by reverse engineering, sort of?
Well, what do we know about linear transformations? So linear transformations take linear combinations to what? The linear combinations, right? So let me just write down a property. Okay? So T of lambda 1 V1 plus lambda 2 V2 is equal to lambda 1 T on V1 plus lambda 2 T on V2. Okay? So what do you think we should do?
So is the vector 6, 3, it's lambda, like it's just the lambda is 3 times the vector or excuse me, lambda 3 times the vector 2, 1.
2, 1. So I'm not sure what 2, 1, where 2, 1 comes in.
Factor out of 3.
Yeah, well, we don't know where 2, 1 goes to either. So I think you have the right idea though. So you're taking 6, 3, right? We know where 1, 5 goes to. We know where 3, 1 goes to. So what do you think we should do with 6, 3? What do you think we should try to do in terms of writing this vector out as?
Maybe we should use the 2 equations at the top and maybe solve for what t as a transformation is.
Take t out of the picture.
You can write it as a linear combination of the other two.
Yes, exactly. So we want to actually write it as a linear combination of the other 2 vectors. Okay, so we want to write this as C1 times 1, 5 plus C2 times 3, 1. All right, so if we find C1 and C2, which make this work, we're in business, right? Because then T of 6, 3 is going to be equal to C1 T on 1, 5 plus C2 times T on 3, 1. Okay? And so if we know what C1 and C2 are, we know where T of C1, 5 goes to, and we know where T of 3, 1 goes to, then we know exactly where T of 6, 3 goes to. Does this make sense? We're going to carry this out on Monday. So the point is that with linear transformations, I'll just write this down. With linear transformations, it is enough to know where finitely many vectors are sent to under, let's call it T. All right? I mean, normally with functions, you don't know, like if you have a function, you know the value of f of 1 and f of 5, you don't know what the value of f of 15 is necessarily, right? So but with linear transformations, if I know where a certain number of vectors goes to, I know where everything goes to after that point. Okay? So this is the real power with linear transformations, is that you only need to have a finite amount of data to explain the whole story. So what we'll do is we'll actually go over this next time, and I'll explicitly find C1 and C2 for you using Gaussian elimination, of course. And then once we do that, we can actually figure out what T of 6 is. Okay, great. Any questions up until this point? Okay, great. So everyone have a good weekend, and please stay safe.
Thank you.
Thank you, Professor.
Okay.
If you just scroll back
Thank you.
up to where you it was like the previous, yeah, just that graph or that, yeah, I didn't get all of it. Thank you.
Great. I will post the notes on the LC this weekend. Yes.
Typically have seats every day, like if I would come in on a different day.
Yes. So I am willing, as long as there's room, if you want to come on the other day. What happens if you see? Fine.
Okay. Because I mean, I kind of like getting out of my apartment more often. So like, if I might just show up.
Yeah.
2 or 3 days a week, I don't know.
Usually there's things.
And if there's not, I can just go downstairs. And look at it.
Okay. Sure, you too. Right. You can go up to 60.